Okay, so here we go. Notes for 3.6 and 8.1. So 3.6 and 8.1 both deal with functions. And as you can see, you've got some homework problems from 3.6, some from 8.1, and I gave you the page number there. So there's not going to be anything too crazy about chapter 8. It actually ends up, I don't know why it's all the way over in chapter 8. So we're describing a relation first. It turns out a function is a special kind of relation that ends up being a pretty big deal in algebra. So a relation in general is a very a pretty general thing. So it is a set of ordered pairs. And if you remember from that very first section we did, we talked about sets, and we talked about a set is just a collection of things. So the things in this particular set are ordered pairs. So here I'm just going to pick some more or less random ordered pairs. I've got 1, 3, 2, -5, and all these are going to be separated by commas. 16, 4, so we'll just do that. And now I'm going to close that set bracket, that curly bracket, and then these are all separated by commas. So this is a set. The set contains 3 items, and each of the items in that set is an ordered pair. So there's 2 big ideas with set range, with relations. The range is the set of all y coordinates. So the set of all y coordinates. So, for example, here, my y coordinates, I have a 3, I have a 5, I have a 4. So the range of this relation is the set containing the numbers 3, -5, and 4. The domain, and domain is something we'll be dealing with a little bit more, and especially if you go on with algebra, there's a lot of stuff you'll talk about with domain. So the domain is the set of all the x coordinates. So I've got a 1, a 2, a 16, the set of all of the x coordinates. So I have 1, 2, and 16. So here is the first example we're going to look at, and this is pretty straightforward. It just says find the domain and the range of this relation. So here's a relation. I've got a set of ordered pairs. I'm going to start by finding the range. So for my range, it's going to be the set of all the y coordinates. And remember, sets don't have repeated elements. So here I have 2, 3, 0, and -2. So nothing was repeated there, so I'm just going to list all of these entries. There I go. So that's the range. That's the list of everything that could possibly show up in the range. Now for my domain, what I want to do is list everything that could possibly show up as an x-coordinate. So I have 0, 3, -1, and 3. So the things that can possibly show up here as x-coordinates are 0, 3, -1, and now 3 is already on that list. So I'm not going to put that in there. And I'll put a little note here. So the note is, do not repeat elements in set notation. So you might want to think about it as that idea that it's a list of everything that could show up and not just writing down every x coordinate. So what we're especially excited about here in 3.6 is a function, and a function turns out to be a really important mathematical concept, and it's a special kind of relation. A function is a relation that assigns to each x value exactly one y value. So exactly one y value. And that is the big concept thing here, is this idea that it's exactly one y value. Now, this is a pretty abstract definition, and it's going to make a lot more sense once we look at a few examples, which I'm going to do here. Okay, so are the following relations functions? So all of these are two sets of ordered pairs, and these down here, these graphs, are also sets of ordered pairs, but we'll talk about those in a minute. So I'm going to illustrate what's really going on with this domain range, and I think this kind of helps it come together. So my domain here, and if you've taken classes with functions before, you've maybe seen this kind of thing. My possible x-coordinates, I have -1, 2, 7, and 8. So this is a picture, this is like a set of all of my different possible x values. And then my range, I've got, let's see, a 1, a 3, 3 again, so I already have 3 written there, and then 6. So I didn't repeat that 3, and that's an important thing. So the set of the domain and the range, that's part of this, but what really makes a relation is that ordered pair aspect, that each of these domain elements are connected to a particular range element. So -1 goes with 1. So I have this. -1 goes with 1. 2 goes with 3. So 2 goes with 3. 7 goes with 3. 7 goes with 3. And then 8 goes with 6. So that's the relation part of it. Now this, the question is this a function? So a function assigns to each x value exactly one y value. So for any x value, so if I say what y value goes with 2, 3 is the only possible answer. What y value goes with 7? 7 goes to 3. 8 just goes to 6. So this is a function, and I'll talk a little bit more about this once we look at an example that is not a function. So this is a function. Every x goes to one y value. And it doesn't matter that two different x values go to the same y value. If I give you an x value, you can tell me what y value it goes to. If I say 2, you can say 3. If I say 7, you say 3. And that's what we want with a function. So let's look at this other example. Here again, I have a domain set. So my domain, I've got 0, 1, and 7. 0 is already on that list, so I'm not going to put it twice. So that's my set of domain elements. Now my set of range elements over here. My range, I've got -2, 5, 3, 7. And now the relation, 0 goes with -2, 0 goes with -2, 1 goes with 5, 0 goes with 3, and 7 goes with 7. Now here, because I have this x value that's assigned to two different y values, this is not a function. So this is not a function because 0 is assigned to -2 and 3. So I think it can help sometimes to think about this, like one thing you really want to be a function is like a bus route. If you get on a bus, you want to know for sure where that bus is going. So for example, here I have, if I get on the -1 bus, I know for sure it's going to go to 1. And it doesn't matter here, these two buses go to the same place. There's all kinds of buses that go to like the Mall of America, and that's fine. If you get on the 2, if you get on the 7, you know where they're going to go, and that's what's important. What you don't want is to get on the 0 bus here and not know if you're going to -2 or 3. You know what I mean? You don't want to like get up for work and maybe you're going to end up at the Mall of America, maybe you're going to end up in, I don't know, downtown St. Paul. So you want these domain elements to go to exactly one thing for a function, and that turns out to be a really important idea in algebra. So predictability is kind of what these functions are about. Okay, here we have a couple more examples, and now these two graphs, these are actually relations. These are sets of ordered pairs. If I look at this is an ordered pair. This is -4, -2. So -4, -2. This is -2, 1. And then this is -1, 1. And this is 1, 2. And you can look at this. Every single x value is getting assigned to exactly one y value. So for just these 4 points, this is the whole part of the relation. If I give you an x value, either that x value isn't assigned to any y value, and that's fine, or that x value is assigned, you can tell me exactly what y value that goes with. So this is a function. This is a function because each x value is assigned to exactly one y value. Now this relation over here, this is again a perfectly good relation. I've got some ordered pairs here. And I'm just going to label them here. I have -2, -3, 2, -1. I have 1, 2, and 1, 3. And so this is not a function because this single x value, when x is equal to 1, that corresponds to y values of both 2 and 3. So if I draw a vertical line through there, through 1, that 1 is getting connected to 2 different y values. So this is not a function. Because 1 is assigned to 2 and 3. And now this idea, this vertical line idea, ends up being really important, and we'll see where that vertical line comes into things on page 2. Okay, so here we have a couple more relations. Now these are just graphs, so these might not look like sets of ordered pairs, but remember what these graphs represent is an infinite collection of ordered pairs that usually satisfy some equation. So these are relations with an infinite number of ordered pairs. And this comes up a lot. And in this case, I can't just write down every single ordered pair, But because every single x value, if you give me an x value, I can tell you exactly what y value it corresponds to. This is a function. So this is a function. And this over here, I have a problem where if I say, hey, what y value corresponds to x equals 3, I get that and that. If I say what corresponds to x equals 4, I get 2 and negative 2. And it only takes one instance of that, of a single x value corresponding to more than one y value, to make this not a function. So this is not a function. So now we talked a little bit last time about the vertical line test, and here if you look at this, I can try to make a nice vertical line here. And that vertical line, there's a bunch of places where I can draw vertical lines and they cross this graph more than once. Crosses more than once, crosses more than once. And that is an example of something that is not a function. And over here too, if I draw vertical lines, I can't possibly draw a vertical line here that intersects this graph more than once. And so that idea is called the vertical line test, which is really nice because it's a relatively easy way to see if something is a function. So if a vertical line can be drawn, if a vertical line can be drawn that intersects a graph more than once, then the graph is not the graph of a function. The graph is not the graph of a function. So here, this graph, I can draw all these vertical lines. Every vertical line I draw intersects it at most one time. This passes the vertical line test. Passes the vertical line test. And if you pass the vertical line test, you are a function. This, however, I can draw vertical lines. It intersects more than once, so this graph fails the vertical line test. Fails the vertical line test. Okay. Now, every linear equation, any line I draw like this, is going to pass the vertical line test except one. So all linear equations pass the vertical line test. Line test. And because they pass the vertical line test, they are functions, and are functions except one. So if you can think about what vertical line would fail the, I gave it away. What linear function would fail the vertical line test? It is a vertical line, except a vertical line. So you've seen a bunch of vertical lines. They have equations like x equals c. And they actually fail the vertical line test as severely as anything ever could. If this is my line, so here's my nice vertical line. I can draw a vertical line that intersects that vertical line at an infinite number of points. So it completely fails the vertical line test. But that is the only linear equation whose graph is not a function and does not pass that vertical line test. Okay, so next we have function notation. And function notation is something that gets used a lot, especially if you keep going with algebra and in applications. It's a pretty big deal. And I'm going to introduce it here. In the equation y equals 2x plus 1, we've talked about this before. This equation is solved for y. Now y is often considered the output of this equation. So like x would be the input, y is the output. So here y is considered the output of the equation. It's also sometimes called the dependent variable or the dependent variable. And x is considered the input. And x is considered the input or independent variable. And I think one way that can help to think about this is very, very frequently the input, like the x here would represent something like time. And so time is just going to keep moving forward no matter what. And if we're tracking like how much money you have or something, the amount of money you have, if it's in some kind of investment, is dependent on time. So we have one thing that's just kind of moving forward that we don't have control over, and we're looking at how this other thing depends on that. So the output depends on the input. When an equation is solved for the output and the equation describes a function, when an equation is solved for the output and the equation describes a function, so I mean the equation passes the vertical line test, then we can use something called function notation. And what we do is we can replace y with this symbol. And this symbol is f parentheses and then x is inside those parentheses. And so what's happening here is I have this symbol that reads f of x, and that is just like y. It's telling me the output, but contained in that notation, it is telling me what variable, what's the name of my independent variable, my input variable. So if I have something like this, f of x, I can rewrite this y equals 2x plus 1 as f of x equals, and I'm just going to leave this open because this is the idea, is this input, this is what I'm going to plug in here. So I have f of equals 2 times like this. And so this is the big idea here, is that, like, don't write anything in here. This is the input. So whatever gets plugged in, whatever I'm plugging in here, and this you can see over here is telling you what to plug in. Whatever I plug in is going to get multiplied by 2, and then 1 is going to get added to it. So this whole thing is going to be the y-coordinate that corresponds to a particular x-coordinate. So let's see what this looks like. Here, for my equation I gave up here, y equals 2x plus 1, f of x is going to be 2 times that input plus 1. If I'm just writing f of x, then my input is just x. So that's what that would be. F of 2, it's saying this is still my function. This is my function structure. And what I'm going to do is, because they're showing me a 2 over here, I'm going to plug a 2 over here, and then I would simplify that. So I get f of 2 equals 4 plus 1, or f of 2 equals 5. And now that, so here I'll go over here, f of 2 equals 5. This has an input of 2, and it has an output of 5. So this corresponds to an ordered pair. So I have an ordered pair. And that ordered pair is 2, 5. So the input of 2 and then the output of 5. And that's the ordered pair that corresponds to this. So the idea is that this and this are kind of two different ways of writing the same thing. So here's a couple more examples. We're going to take and look at some different inputs for this particular function that's described as g. Okay, so here, g of 2, and people get in a lot of trouble with negative signs here. So remember what that function is doing. What g of x does is it takes whatever the input is, squares it, and then subtracts 3. So now the input I'm given here is 2, so I'm going to plug 2 in there, and now I end up with 2 times 2 is 4, so g of 2 equals 2 squared is 4 minus 3, and now I'm just going to do that subtraction, so I have g of 2 equals 1. And then I was also asked here, find those values and then write the corresponding ordered pair. So the corresponding ordered pair is 2, 1. Now over here, what this function is going to do is take some input, square it, and then subtract 3. So the input I'm given now is negative 2. So I put that negative 2 in there. And now remember that negative 2, that whole thing is getting squared. So what's happening here is negative 2 times negative 2. So I end up with g of negative 2 equals negative 2 times negative 2 is positive 4 minus 3. And I end up with g of negative 2 equals 1. And that gives me an ordered pair, negative 2, 1. And over here I have g of 0, so it's going to take whatever that input is, square it, subtract 3, and now I'm just going to plug in 0, and this is nice, working with 0 is always great. G of 0 equals 0 minus 3, so g of 0 equals negative 3, and that gives me a ordered pair of 0, negative 3. Okay, on the next page we'll talk about some line applications with functions. Okay, so here, and I'm going to give you some x values here. So we're going to look at x equals negative 3, x equals 0, and x equals 2. And what we're going to do is using this function idea to graph some linear equations, all I'm going to do is take, so for this first one I have two different functions, and I'm going to do this first one and then I'll have you guys do the second one. But here for f, I have f, that's some function. What it does is it takes an input and multiplies it by 2. So my first input that I'm given here is negative 3. And so what I end up with is f of negative 3 equals negative 6. So that gives me an ordered pair, negative 3, negative 6. So I have negative 3, negative 6. I'll put that right about there. And now I have f of my next input, and the function does the same thing. So now my input is 0. I plug in that 0, and I get f of 0 equals 0. So that gives me an ordered pair 0, 0. I can graph that. And then I have f of 2. So f of 2 equals 2 times that input, which is also 2. So I'm going to plug in that 2. And what I end up with then is f of 2 equals 4. So that gives me the point 2, 4. There we go. And now I can just draw the straightest line I can through those points. There we go. So that is my line. And you should always put those little arrows on the end so I know that you know that it goes on forever. So what you're going to do is do the same thing for this second equation. And I'm going to talk a little bit about this next problem here. Okay, find an equation of the line with slope -3 and y-intercept of 0, -5. Write this equation using function notation. So kind of a lot of these problems are going to be they're just going to be problems like earlier in chapter 3. So here I have m, this is my slope, is -3, m equals -3. And now this is exciting because sometimes they give me a second point and it's not very helpful. Or I have to use that point slope. But this is the y-intercept, and since it is the y-intercept, that means this is my b. So I can go straight to my equation, my slope-intercept form, y equals mx plus b. And I have everything I need. So my equation is just going to be y equals -3 x plus my y-intercept is -5. So I really should then simplify this a little bit to y equals -3x minus 5. And now this is my equation. So this is like what we had talked about before. So this is an equation for the line. And the only thing that makes this different from a 3.4, 3.5 problem is they now want it in function notation. So all I'm going to do is replace that y symbol with f of x, and then leave the rest of it the same. So to convert to function notation, replace the y symbol with the f of x symbol. Okay, and then on the next page, there's some problems, some group problems, so I'd like you guys to do those. I'll put the answers on D2L. Definitely, you can do those in some of the tutoring sessions or talk to other people in the class. And as always, let me know if you have any questions.